An exceptional piece. I actually was like scrambling to find a piece because some of them are just wonderful because they're these nice deep red with white spots or white splotches. Now, this stuff's going to be pretty flat, like the remainder, like what we see on this side of the lake. Starting from what we can see as Mount Bohemia there, which is actually an andesite rhyolitic body, this is all Jacobsville sandstone. The flat part you see coming in, the fog is kind of nice, it's accenting the Jacobsville sandstone juxtaposed to the Portage Lake volcanics. Now these were basalts that formed about 1.1 billion years ago as a mid-continent rift. There was a hot spot similar to what we see in Hawaii today. They kind of made the crust very plastic, very thinned it and made it more easily to break apart. And it created this huge rift that went all the way from about St. Louis all the way up around Lake Superior, almost down to Detroit, kind of making an arc. So Lake Superior is actually formed in the basin of that rift. Now, during this rift process, magma oceans were pouring out onto the surface. Now these eruptions are very similar to the ones that we see in Hawaii today, but these were at a massive scale. And to give you an idea, I mean, the cooling is how we can tell the scale of these flows, because the flows that are currently happening in Hawaii, those things are going to cool in a month or two. You know, the flows that were happening during this time took 1,000 years to cool.
Wow.
And that is one of the hallmark signatures of the Keweenaw basalts that we see, because there's very large crystals, phenocrystals as we call them, and we also host, which is really something I love to boast about, we also have the largest flow on Earth, the largest lava flow on Earth, which is the greenstone flow, and that is of course by volume and thickness. And thickness is really important because the thicker the lava flow is, the bigger the crystals are in the center, and sometimes, you know, we get really special things like native copper forming here. So what we're looking at here, sandstone, basalt, and the dividing line between them is going to be the Keweenaw Fault. So we have 940 million year old sandstones that we're currently on. And this stuff is a little bit softer, a little bit more erodible. Then we have 1.1 billion years old, so there's, you know, some missing time there. And actually, let me see, I have this great book, if you're not aware of this, this is put out by Erica and Bill Rose. Erica Vi and Bill Rose. And they have a wonderful fit, you know, actually I will go ahead and pass a couple of these around on this page, just to kind of give you an idea of what we're looking at. So you can kind of get an idea of what I am talking about. Where is that other picture of Gratiot Lake? Okay, if you want to, actually, yeah. Robin, I think you're pretty familiar with the book.
Yes,
so,
it's wonderful.
And this is just an incredible place, because why is this lake here? I mean, we're sitting in a flat sandstone. We've got these really old basalts right here too. Why is this here? And there's two major reasons. One, the fault. The fault has basically pushed up older rocks on top of younger rocks due to plate tectonic forces. And also
pushed up
so as the plates were kind of accreting onto each other in North America, in the North American continent, things were just getting pushed onto each other, onto each other. So it pushes up these very large rocks, creating a thrust
this
fault,
rift
which would be the ridges that we're seeing.
Yeah.
Those are going to be uplifted, and the sandstone is going to be, which would have been up here,
like sucked down with the push up of this.
So, because they're also softer too, so they're going to allow a little bit of this movement to happen. That's one factor. The second factor is glaciation. So we had, at one point, actually at 4 distinct periods, we had 1 mile to 2 miles thick of ice sheet covering this land. And not only was it covering it, but it was shaping it. These were glacial advances and retreats, and those are very well documented in the rock records. But you can look at certain erosional features like scours in the rocks and glacial grooves. You can also see things that are going to be more depositional, like kettles, moraines, and till. And also what we'll hopefully will see over it is glacial erratics, which are one of my favorite things to find, especially when you're doing GIS mapping, because they rarely move.
Okay.
So you can find a glacial erratic from 1938 and in 2016, and it hasn't moved, which is pretty great. But yeah, if you can imagine about a mile up ice in the cascading waterfall, specifically in this end of the lake. Now I want you to take a look at your bathymetry map, the fishing map, and that's going to have you're going to see at the very north end there is a much deeper, and there's a very sharp cutoff. Now, if any of you have ever visited a waterfall, have ever swam in a pool like that, a plunge pool is exactly what we are, and this is at a gigantic scale. This is at a gigantic scale because this thing goes down. It says 70 feet on there, but I think I've heard estimates of 90, right?
I think I've marked that.
It does. This is an old map, but usually we find a spot that's around 72,
73, sometimes.
Yeah.
It depends on lake level too.
It does, and it
Sure.
absolutely
You know,
depends
and
on
the
lake
is
level.
down
Mm-hmm.
there. But it's a little closer to shore. We're not right over that, are we, Jim? How
No.
deep is it here?
It's 29.
So do you want
It
us to
was
go in a little
teens
closer?
back
We
there
should go
on the
in.
way.
closer
Yeah, we can move.
to
We can start
now
moving
is
in
the time
closer,
to
and
go
then we'll
closer.
just.
See if you can find
And
a really
if you haven't visited a plunge pool or waterfall that has a really nice deep plunge pool, a really good analogy to that would be when rain falls off your roof and kind of creates little divots in the ground when it hits. That's pretty much exactly what we're looking at. And as you can see, we have the fault going through here, and then we have a series of little pools. And so we're Torch Lake. I'm not sure what that is. Actually, pond.
Fair?
Yeah.
Fair Lake?
Fair Lake. Then we have Lac La Belle, Deer Lake, Gratiot Lake. These are all plunge pools, or they've been theorized to be plunge pools. Which, if you can imagine, the rocks here are much more resistant. The basalts, the old lava flows are much more resistant, and so they're going to stand up to the ice. They're going to be like, no, you're going to move around here. Whereas with the sandstone that we're on, it is easily eroded off.
Sure.
So the glaciers took away basically. Oh wow! And the fact that these were deposited, as the formation was 940 million years ago, it removed that much sediment and took it away, deposited and as glacial moraines and till. So